Hi, everybody. So first of all, you'll have to excuse any background noise that happens. I'm holding the iPad in my hand as I'm filming this. I thought it would be a good idea to film a quick video to kind of walk you through some sample calculations that you might encounter in this week's specific heat lab. The concept that we're trying to bring home is the idea that the specific heat capacity of a given substance is a characteristic property of that substance. That is, no matter how much you have, it's always going to take the same amount of heat energy to raise the temperature of 1 gram of that substance by 1 degree Celsius. And we're actually using the concept of conservation of energy to allow us to do that. So we're making some assumptions here, namely that the amount of heat that is gained by a container of room temperature water, which you had in your calorimeter, your styrofoam cup in the experiment, is equal to the amount of heat given off by a piece of metal that we had in a warm water bath. And so we have some sample data here. This may be similar to what you had, but obviously you're going to want to calculate it with your own data. So let's take a scenario where we had an initial temp of water of 24.3 degrees Celsius. That's about the room temperature in our classrooms. And the initial temperature of the metal would have been somewhere close to 100 degrees Celsius because we had it soaking in a beaker full of boiling water. So I used 95.5 degrees Celsius as a sample data point. And the way it works is that the hot metal will transfer its heat to the cooler water. That's the second law of thermodynamics. And eventually, those two systems will reach thermal equilibrium. And we'll know that they're at their thermal equilibrium when the temperature stops rising. And so in this particular scenario, the final temperature is equal to 30.2 degrees Celsius. And so I went ahead, because I know I'm going to need them in the specific heat equations to follow, I went ahead and calculated delta T, the change in temperature, and you'll remember that we calculate that by taking the final temperature and subtracting the initial temperature. And so for water, the temperature rose by 5.9 degrees Celsius. And actually, I have a small typo here. We should add a negative sign. Hopefully you see that. And delta T for the metal is equal to negative 65.3 degrees Celsius. And that reflects the fact that the temperature of the metal decreased during the course of the experiment. So, again, we're going to use the concept of conservation of energy here, and we are going to first calculate the amount of heat that is gained by the water. We can do that because we know the specific heat of water. It's 4.18 joules per gram degree Celsius. So, since we know the mass that we started with, and we know the specific heat of water, and we can also calculate delta T, we already did up above, we can go ahead and calculate Q, which is the amount of heat that is gained by the water. So I'm going to go ahead and do this down at the bottom here. And we have a mass. In the lab, we started with a mass of 100 grams. So I'm going to go ahead and use 100.0. And we know that the specific heat is 4.18 joules per gram degree Celsius. I should put 100 grams here. And then we know that the temperature change is 5.9 degrees Celsius. And so when we calculate all those numbers out, I probably should have already calculated these numbers, but you'll have to give me a minute to hit up my calculator in the background. 100 times 4.18 times 5.9 gives us, I'm going to go ahead and round to 3 sig figs here and say that that water absorbed 2,470 joules of energy. So that is the amount of energy that was gained by the water. And of course, since we had a relatively closed system, we had a piece of hot metal inside that room temperature water. The only place that water could have gained that energy is from the metal. And so we can assume that right here, the Q of the water, the amount of heat gained by the water, is equal to the opposite of the amount of heat is equal to the amount of heat lost by the metal. That's the reason we use a negative sign for Q in that particular case, because it's an exothermic process in which energy is released by the metal. So we know that the Q of the metal is equal to 2,470 joules. Now, in reality, there was some energy lost, but we sort of have to assume, for the sake of the experiment, that all of the energy from the metal was transferred to the water. So we know Q in this particular case. We know M. M was typically around 64, 65 grams for the samples that we used in the lab. So I'm going to go ahead and use 65.23 grams as a mass for our mystery metal. And ultimately, in this case, it doesn't really matter what the metal is. Then we know that we're solving for C. We don't know the specific heat yet, but we do know delta T. Delta T was equal to 65.3 degrees, negative 65.3, because we lost, the temperature went down over time. So we know that if we rearrange the equation for specific heat, we end up with C on one side, and then we take Q, we divide by M times delta T. So if I put these numbers down below, we have negative 2470 on top, and on the bottom we have 65.23. Sorry about the decimal points. It's a little hard with the stylus to make that happen. And 65.3 degrees Celsius. Put a negative sign in there. Now, the specific heat should always be a positive number because that signifies the amount of energy we have to put into a system to raise its temperature. So that's always going to be a positive quantity. 24, let's see. So we're going to multiply what's on the bottom, and we're going to get, and this is just for reference, sorry about muddling it up a bit, 4259.519 is what we get on the bottom. And we're going to divide 2470 by that. And we are going to end up, and I'm going to go ahead and round to 2 decimal places here. The specific heat of this metal is going to equal 0.58 joules per gram degree Celsius. So again, this is a 2-step process. We're going to know the mass, the specific heat, and the temperature change of water. And we're going to use that to determine the amount of heat that was gained by the water. And since we know that the heat that was gained by the water came from the metal, when the metal transferred heat to the water, we can set that quantity equal to the amount of heat lost by the metal, and we can use what else we know about that metal, namely its mass and the temperature change that occurred during the experiment, to find C, which is the specific heat capacity of that metal. So, I hope that's helpful. If you have any questions, talk to me or any of your teachers, and have a great day.